You remember up to this point. Just one technical terminology that I forgot to introduce when I was talking about this is, for some reason, we call this part the lower Hubbard band, and that is the upper Hubbard band. It has something to do with a particular many-body Hamiltonian that is often used to describe transition metal and transition metal compounds. And when you solve that, essentially, this picture that I have brought out more pictorially and intuitively for you emerges, and this is, so these are called Hubbard bands attributed to Mr. Hubbard, and this being the lower of the two, it's called the lower Hubbard band. That's our Hubbard. So the energetics that are important here are U, the Coulomb interaction strength that separates the upper Hubbard band from the lower Hubbard band, which splits essentially this D state into two parts, and the bandwidth that is controlled by the hopping between the sides, which is W. So these are two energies that are important. And you have seen that it's U approximately equal to W that marks the boundary between the metal and the insulator. If U is smaller than W, it's a metal. If U is larger than W, it's an insulator. Okay. So this part is what I would like you to remember. On to now the next part that I'm going to talk about. The next part that I'm going to talk about is that so far I've never talked about oxide. I was talking about transition metal. I put only one kind of element, hydrogen everywhere or Dn electrons at every side. There was no oxygen in there. But I wanted to talk about oxide, and now I must bring in the oxide. So what is going to be the minimum model? I would always like to do the most minimalistic approach, not bring in any additional complication that is not required to understand the phenomena that I want to understand. So when I'm saying oxide, obviously, I cannot say just with transition metal D states. I need to bring in the oxygen P states also. And you'll very soon see why it becomes actually quite critical. One could have said, okay, ignore the oxygen P states altogether and only talk about transition metal D states, because oxygen P state is always fully filled in an oxide. Because you know oxygen forms O2 minus ion, and oxygen 2 minus ion corresponds to 2p6. And since the P level can take only 6 electrons, 6 electrons are already there in the oxygen 2 minus ion, 2p6. So it's always a filled orbital. And if it is a filled orbital, it's uninteresting. And you can ignore it. You will see why that is not possible, and we need to have the oxygen. Having assumed that oxygen P, we need to ask, so what happens to the D? Remember, D is the one which is Coulomb interaction is large. I talked about it because the D level, the wave function is not very spread in the space, and so they're narrow, and that's why they're interacting with each other very strongly. In fact, that is one of the reasons, the equation that came in the morning in sort of stop, that in non-hydrogenic atom, why does it sequence itself as SPDF? Remember, if U was equal to 0, if electron-electron interaction was 0, every problem is a hydrogenic problem, and then SPD would have exactly the same energy. It is the Coulomb interaction that distinguishes them, and that Coulomb interaction strength is larger as you go from SP to D to F, and that's what pushes up the energy of P above S and D above P and F above B. Okay? And that's why in the transition metal D, the Coulomb interaction is very important, so we'll not ignore the Coulomb interaction strength and keep at U not equal to 0. What about the P? We'll start with the simplest model where Coulomb interaction in the oxygen P will consider it to be 0. Say it's not very high, which is not quite correct, but it turns out that there are ways to take into account the effect of Coulomb interaction within P without going to the complication of going away from this assumption. And if I have the occasion, I'll point that out later. Actually, it's in some very peculiar way ends up changing the value of U at the D site to simulate the effect of U here while retaining the model equal to 0 for the oxygen P. It's a very strange way of thinking about it, right? But it works, and that model works. But I need to ask a question. I've said that D level, the epsilon D, or the epsilon was the energy, but now that I have two levels, D and P, I have to ask, where is the P level with respect to the D level? Which means I need another new energy scale that measures the energy difference between the D level and the P level. This is the one that we call the charge transfer energy. It is essentially the energy that is needed to transfer, even in the absence of any hopping. If I want to take an electron from transition metal D, from oxygen P, and put it into the transition metal D side, how much energy does it cost? It basically measures the energy difference between the P and the D in some sense. And that's the charge transfer energy. So this is the only new element that's going to come in. Besides the various hopping interaction string that I've already talked about, which will determine the W, the U, the Coulomb interaction within the D that I've already talked about. The only other new thing that's going to come in is this energy scale associated with transferring electron between D and P state. Remember, transferring electron between D and D state cost me no energy because both were epsilon D. But this has an energy, and that I must take into account. And then, after having understood these parts, I should be able to ask the question, when is a transition metal oxide going to be a metal or an insulator? And we'll proceed with the kind of pictorial approach we have had so far. And the pictorial approach is that let's put the oxygen 2p, I said. Oxygen 2p is fully filled, right? Because it has 6 electrons. All the oxygens have 6 electrons. The 2p band is fully filled. So here's the 2p band. It has formed the band because there are infinity of them and there's hopping interaction. And the Coulomb interaction is 0. So that's why it's not split into two parts and it's completely filled. Now I'm going to bring in the D level. The D level has the Coulomb interaction, which has split it into two parts, the lower Hubbard band, the upper Hubbard band. The lower Hubbard band is fully filled, the upper Hubbard band is empty. And whether there will be a finite gap or not depends on whether U, which is the energy between the center of these two, is larger than the bandwidth or not. Here I have drawn in a way that there is a gap between. That means the U is larger than U critical, which is equal to the bandwidth. And I have deliberately put this energy in such a way. Now let's mark the energies. That's the band gap, you can see, because these are all filled. That's the first empty state. Band gap is rigorously defined as the energy difference between the top of the occupied level to the bottom of the unoccupied level. Coulomb interaction strength, it is the energy between these two levels, the U. Delta is the energy required to take one electron from here and put it there, as we have already defined. Right? That's a new energy scale that I have got in, delta. Charge transfer energy. It's called charge transfer energy because I'm transferring a charge from oxygen to transition. And this is an insulator. Starting with exactly the same description, if my U becomes small, then those two pieces will overlap with each other and it will become a metal just the way you had seen earlier. U becomes smaller than the critical value, which is the bandwidth. Oxygen P is only a spectator orbital. I don't even have to consider it. This description is exactly what I had talked about earlier. And I understand when I get an insulator and when I get a metal. This is called the Mott-Hubbard insulator, as I told you. This is in the limit where delta is much larger than U, so it's below, because delta is much larger. So actually it has very little effect. U is larger than W, or which is equal to critical, U critical. And so I have a gap, Eg. You can see Eg in this limit is actually controlled by U. As U changes, Eg will change, because Eg is equal to U minus W. In this limit, delta is still much larger than U, but this U has become smaller than the critical value, so it has become a metal. So this is called a Mott-Hubbard insulator, after the name of Hubbard, who originally gave the Hamiltonian, and Mott, who provided this pictorial kind of similar, not exactly this, similar kind of interpretations. This is called a DD metal, not because I love it, but because these two, you can see this is a D piece and this is a D piece. The two D pieces overlap. So essentially the conduction is because a D electron from one side of D can hop to another side of D and conduct itself, because it's not strongly correlated. The bandwidth is larger than the Coulomb interaction strength. So it doesn't mind paying the price of going to another transition metal site and increasing the Coulomb interaction energy by U, because the bandwidth more than compensates that energy. And so it becomes a metal. So it's called a DD metal. But I may have a different situation. Earlier, in this case, delta is larger than U. But I can have U larger than delta. If U happens to be larger than delta, you can see now that U is this much and delta is that much. Immediately you can see that oxygen has a very important role to play, because now the conduction gap is measured not from D level to D level, but oxygen P to D. That means for conduction, the lowest energy excitation required takes an oxygen electron and puts into the transition P D level. So that's why it's called a charge transfer insulator. That is, a band gap or the minimum excitation is of a charge transfer kind, where an electron from oxygen has to be transferred to the transition metal side. This happens in the limit when U is larger than delta, as shown. And that delta is larger than some critical delta, because now if delta, starting from exactly the same thing, if the delta becomes small and that overlapped, then I get a metal. But you see, now the metal, that those electrons that conduct have both P and D characters simultaneously. And so we call them the PD metal, because that has both P and D characters. So if in this limit U is greater than delta and delta is greater than some critical delta, I have an insulator of a kind that I call charge transfer insulator to separate it from Mott-Hubbard insulator. Here the band gap is not controlled by U, because if you change U, all that would happen, that piece will move down or up, but nothing would happen between this gap. This gap is controlled by delta. In the earlier picture, if I change delta, nothing would have happened to that band gap. So here the band gap is controlled by delta, and that's why you call it the charge transfer insulator. And that was Mott-Hubbard insulator. That time it was DD metal, because this and that piece overlap. But here we call it the PD metal, because the charge carriers have both mixed P and D character. That tells you what the phase diagram is like. This is an actual calculation and a very, very famous phase diagram called ZSA phase diagram, associated with the three authors who proposed this, Zanen, Sawatsky, Allen. Fairly complex looking thing, but it's very simple to think of. This is a charge transfer energy, delta. This is the Coulomb interaction energy, U. You know that when both U and delta are large, then you have an insulator. Because U is large, the upper Hubbard band and lower Hubbard band are separated, and delta is also large, so oxygen P is also separated from the upper Hubbard band. So as long as both U and delta are large in this direction, these parts are all insulated. But there is a critical value of U. This is U. See, this is a critical value of U. If I go below that value of U, independent of delta, what would happen? Lower Hubbard and upper Hubbard band will overlap. Because U has become very small, so that upper Hubbard band and lower Hubbard band will overlap, and it will give a metal. So for small U, there is always a metallic phase. When U becomes large, it becomes insulating. And that U large is where the gap is controlled by Coulomb interaction, and that's a Mott-Hubbard insulator. There is this 0, which corresponds to, okay, imagine this line. This line measures that critical delta, below which you always have a metal, because oxygen P and the upper Hubbard band have overlapped. If delta is smaller than that, than this vertical line, almost vertical line, then you get always a metal in this case, simply because upper Hubbard band has overlapped, which is unoccupied, has overlapped with the occupied oxygen P band. But as long as delta is larger than that critical value, you get an insulator. In that insulating state, the gap is proportional to the charge transfer energy. So that's the charge transfer insulator, and this is the, you have the metal which has character of P and D together because delta has become very small. There is the approximately 45 degrees line which separates on this side the Mott-Hubbard insulator, and that's the charge transfer insulator. This is the D metal, this is the PD metal. So the transition metal oxides, every kind of transition metal oxides will more or less map onto this phase diagram. With some twists, and one of the twists is what we had shown some days back. But again, to remind you, what you just now saw here is summary of what I have already shown you. The D metal part, which is this part, is metal because you see Coulomb interaction strength is smaller than this critical value, lower than that. And that's where these two overlap. And you get a D metal.
What is this strip around the 45 degree line?
That is the one that separates between this is the Mott-Hubbard insulator where the gap is between upper Hubbard and lower Hubbard, and the charge transfer insulator where the gap is between the upper Hubbard and the oxygen P. E equal to delta actually will make both of them identical because this piece will then come and sit here. That gap will be given by here as well as here will be equal. So 45 degrees is E equal to delta line. When U is larger than delta, that means this piece is below the oxygen P. So this is irrelevant, the gap is between these two. So the gap is controlled by delta. That's a charge transfer insulator. And when delta is larger than U, like here, then oxygen 2P is irrelevant, the gap is defined here, controlled by U, so the gap is proportional. 45 degrees is approximately the line that separates these two, approximately. But this is not a phase line, in the sense that there is no phase transition from one to the other. These are only descriptive language. Please understand, though, there is a phase transition here, the insulator becomes metal, there's a phase transition here and the insulator becomes metal. This 45 degrees line going across is a continuous change, there's no change of phase. So basically, if you are far away from this, for example, you are here, your gap is almost completely controlled by Coulomb interaction and weakly controlled by the charge transfer energy. If you are here, then the gap is almost completely controlled by delta and weakly controlled by U. As you keep changing, that continuously changes. It's a continuous change, there is no difference in phase. Okay? There is no phase transition across. And in this limit, you get this PD metal where the delta becomes less than delta. But it so turns out that if you did the calculation right, because in